Hello students, today I am going to discuss important topics from Unit 8, Dual Nature of Radiation and Matter. The first important topic is photoelectric effect. So what is photoelectric effect? So when radiation falls on any photosensitive material or metals, it ejects electron from the metal surface. Let's see with some example. Okay, the light from the source falls on photoelectric material, it ejects electron from the metal surface. Here we can use light or any other electromagnetic radiations. See here, whenever the radiation falls on a photosensitive material, electrons are ejected and it reaches the anode. So this effect is called photoelectric effect. When the photoelectric material irradiated with any electromagnetic radiation, it will eject the electron from the metal surface. The emitted electron is called photoelectrons and the current due to the photoelectrons is called photoelectric current, and this effect is called photoelectric effect. Okay, the next topic is laws of photoelectric effect. The first statement, first law is, for a given frequency of incident light, the number of photoelectrons emitted is directly proportional to intensity of incident radiation. See here, radiation falls on, whenever the radiation falls on a cathode, that is a photosensitive material, it will eject the electron from the metal surface. This effect is called photoelectric effect. This the current due to the photoelectron is called photoelectric current. So when you increase the intensity of incident radiation, intensity means brightness. So when you increase the intensity of incident radiation, the number of photoelectrons emitted also will increase. When the number of photoelectrons increase, the photoelectric current also will increase. So this is the first statement. In this case, the incident radiation must have a minimum frequency. So if the frequency is below that minimum frequency, then the photoelectron will not be emitted from the metal surface. And then the second statement is, maximum kinetic energy of photoelectron emitted from a given metal is directly proportional to frequency of incident light. The maximum kinetic energy of photoelectron, it depends only the frequency of incident radiation and it is independent of intensity. So when you increase the intensity, here the stopping potential for different intensity is same. So increasing intensity will not create any effect on stopping potential of the photoelectron, so photoelectric current. But when you increase the frequency, that also increases the stopping potential. So the maximum kinetic energy of photoelectron, it depends only the frequency of incident radiation and it is independent of intensity of incident radiation. Here the third statement is, maximum kinetic energy of photoelectron, it is independent of intensity of incident radiation. And then fourth one, for a given surface, the emission of photoelectron takes place only if the frequency of incident radiation is greater than certain minimum frequency. So the incident radiation must have a minimum frequency. That frequency is called threshold frequency, below which, if the incident radiation has a frequency below that threshold frequency, no photoelectrons are emitted. If the incident radiation has a frequency greater than threshold frequency, then the photoelectrons are emitted from the metal surface. So there is a frequency of incident radiation is called threshold frequency, below which there is no emission of photoelectrons, above which photoelectrons are emitted. And then the fifth statement is, there is no time lag between incident of light and ejection of electrons. Here, when the radiation falls on a photosensitive material, electrons are ejected. Here the incident of incident radiation and emitted photoelectron is an instantaneous process. So, there is no time lag. There is no time lag between incident radiation and the emitted photoelectrons, and this effect also proves that light is a particle, because if the incident radiation is a wave, then the electron will take much time to get energy from the entire wave. Okay, these are the laws of photoelectric effect. So, there are 5 statements. Okay, the next topic is Einstein's explanation of photoelectric equation. Albert Einstein, the year 1905, he applied quantum theory successfully in photoelectric effect. So, according to quantum theory, energy is propagated as a wave packets, and each wave packet has an energy is equal to h nu. So, Einstein called them as photon. So, in this case, light travels as a particle. So, each particle having the energy is equal to h nu. Here the name of the particle is photon. Okay. When radiation falls on photosensitive material, it will eject the electron from the metal surface. Okay. Here the energy of the photon, it is used to eject the electron from the metal surface. How this energy of the photon utilized in photoelectric effect? Let us see, here h nu is the energy of the photon. When the photon strikes the metal, it ejects the electron from the metal surface. So, in order to remove the electron from the metal surface, we need a minimum energy. That minimum energy is called work function of the metal. Here we are going to use the symbol phi or phi naught. Here phi is nothing but the work function, the minimum energy required to liberate electron from the metal surface or to remove the electron from the metal surface. So, the incident photon, first it ejects the electron, some amount of energy it is used to eject the electron from the metal surface, and the remaining amount of energy, and that is used to impart the kinetic energy to the electrons. So, of m v square. So, h nu is the energy of the photon. Here some amount of energy it is used to remove the electron from the metal surface, that is called work function, and remaining amount of energy it is used to impart the kinetic energy to the electrons. So, this is called Einstein photoelectric equation. Okay. In this case, what is the value of work function? The minimum energy required to liberate an electron from the metal surface. Okay. Let us see, let us consider the photoelectric effect at threshold frequency. At threshold frequency nu naught. What is threshold frequency? Is the minimum frequency below which there is no emission of photoelectrons, above which photoelectrons are emitted. So, nu naught is the minimum frequency. See, at threshold frequency electrons are just ejected, but the kinetic energy of electron is 0. At threshold frequency, when the radiation falls on a photosensitive material, electrons are ejected, but it will not reach the anode because the kinetic energy of electron is 0. It just ejected at threshold frequency. So, that the kinetic energy of the electron, it is equal to 0 at threshold frequency. Kinetic energy, that is equal to 0. So, that the velocity of the electron will become 0, so that of mg square value will become 0. At threshold frequency, h nu naught is equal to phi naught. So, this term will become 0 because the velocity of the electron is 0. So, at threshold frequency the velocity of the electron is 0 because it is just ejected, but it will not reach the anode. Okay, here the kinetic energy is 0 because the velocity of the electron is 0. So, here at threshold frequency h nu naught, here nu naught represents threshold frequency equal to phi naught. So, this is the minimum energy required to liberate an electron from the metal surface. Now you substitute this equation in the above equation, so that we will get h nu is equal to h nu naught plus half m v square, half m v square. So this is also called Einstein photoelectric equation. Okay. If the emitted electrons does not lose energy due to the collision, then the entire energy of the electron will be kinetic energy. If there is no energy loss during the emission of electron from the metal surface due to the collision, then the emitted electron will have fully kinetic energy, so that the electron will travel with the maximum velocity. So in this case, we can write the kinetic energy of electron. Here half mv square is the kinetic energy, half m v square. In this case, the electron travels with the maximum velocity, so that we can write v maximum, half m v maximum square, that is equal to h nu, and bring this term to the left hand side, so that it will become minus h nu naught. Here we can take h common, nu minus nu naught, and we also can write it in another form. Instead of h nu naught, we can write phi naught. So the maximum kinetic energy of m v max square, this is equal to h nu. Instead of h nu naught, I am going to write h nu naught is nothing but phi naught. So minus phi naught. So this is the maximum kinetic energy. This also can be written as k max. So k max is nothing but maximum kinetic energy of the electron, that is equal to h nu minus phi naught. Okay. So here you can see the minimum energy. So this is the h nu naught is the minimum energy. At threshold frequency, the electrons are just ejected, but the kinetic energy of the electron is 0, because the velocity of the electron is 0. So here h nu naught is the minimum energy or the work function of the metal. So Millikan experimentally verified Einstein photoelectric equation. When you plot a graph between frequency and maximum kinetic energy for different metals, we will get a different work function. For cesium, the work function is 2.14, for potassium 2.30, for sodium 2.75, and calcium 3.20. Slope of the graph, it gives value of Planck constant. It is independent of the material. The Planck constant, it is independent of the material. So slope value, that is equal to Planck constant. For example, slope is equal to AB by BC. This value equal to the Planck constant. The value of Planck constant is 6.626 in 10 power minus 34 joules second. So it is independent of the material, where Planck constant is independent of the material. Okay, the next topic is photoelectric cells. So what is photoelectric cell? Photoelectric cell is a device, it converts light energy into electrical energy. Okay, so there are three types of photoelectric cells. One is a photoemissive cell, and second one is photovoltaic cell, and third one is photoconductive cells. So photoemissive cells, so whenever radiation falls on a photosensitive material, it will eject the electron from the metal surface. Okay, photoemissive cells, it emits the electron when radiation falls on photosensitive material. And photovoltaic cells, it means when radiation falls on a metallic surface, it will produce a corresponding voltage difference. So here the intensity of radiation is directly proportional to the voltage. And the third one is when radiation falls on a photosensitive material, the resistance of the material will decrease. The resistance of the material will decrease, so that the conductivity will increase. That is why the name is called photoconductive cells. So when radiation falls on a photosensitive material, here the resistance of the material will decrease, so that the conductivity will increase. So now we are going to discuss about photoemissive cell. The photoemissive cells it consists of a quartz bulb, evacuated quartz bulb, in which a semi-cylindrical cathode is placed, and a thin wire or thin rod will act as a anode. So, this is the cathode and this is the anode. Okay. And these cathode and anodes are connected in series with battery, rheostat and a galvanometer. See here, when radiation falls on a cathode, it ejects the electron from the cathode, because the cathode it is coated with low work function material. For example, cesium oxide, it has a very low work function. When you apply a minimum amount of energy, we can liberate more number of electrons from the metal surface. So, here the cathode it is coated with low work function material. So, whenever radiation falls on the cathode and it ejects the electron, and emitted electrons are attracted by anode, and due to the flow of this photoelectrons, there is a current flows in the circuit that we can determine using galvanometer. Here the photoelectric current it depends intensity of incident radiation, and it depends the potential difference between the two electrodes. Okay, the next topic is de Broglie wavelength. So, in the year 1924, de Broglie extended the wave particle duality theory. From the fifth lesson already Maxwell proposed that light travels as a transverse wave. Light is a transverse wave and its wave nature is transverse. So, according to Maxwell, light is a wave. Here, according to Einstein, light behaves like a photon, is a particle. See here, if a radiation can behave like a particle, if a wave can behave like a particle, why can't a particle can behave like a wave? That is a question of de Broglie. So, that it derived an expression for wavelength of electron. So, we all know that according to Einstein, the NH is equal to mc square, and from the quantum theory, the energy of the photon quanta E is equal to h nu. Here we can relate these two NH. So, instead of E, you can substitute mc square. So, mc square h nu. Here we can substitute the nu value, nu is equal to c by lambda. So, mc square h c by lambda, here we can cancel one c c. So, mc is equal to h by lambda. We need wavelength, so that rearrange the expression for wavelength, where lambda is equal to h by mc. Here c is the velocity of light, but we are discussing about the particle. So, a particle cannot travel with the speed of light, so that here we can replace the c with v. So, lambda is equal to h by mv, where v is the velocity. So, we all know that the product of mass into velocity is nothing but momentum. So, lambda is equal to h by p. So, according to de Broglie, if radiation can behave like a particle, why can't a particle can behave like a wave? So, he thought all the particles it behaves like a wave, and he derived the wavelength of matter particle, that is a wavelength of the matter particle lambda is equal to h by p, or lambda is equal to h by mv. So, by using this relation we also can determine the wavelength of electron. Okay, the next topic is de Broglie wavelength of electron. Okay. See here, in the case of photoelectric effect, when you apply negative potential to the anode, for a particular potential we can stop the emission of photoelectron, so that the photoelectric current will become 0. That potential is called stopping potential. So that in order to prevent the emission of electron from the metal surface, we have to do the work done. So that work done is nothing but potential into charge, EV. So work done, this is equal to kinetic energy of the electron of mv square. So here we have to do the work done. That work done should be equal to the kinetic energy. Okay. So from this equation we can get the velocity of the electron, that is v square. So v square is equal to VE. Here capital V is a potential and small v is velocity. So v square is equal to VE divided by m. So when you remove the square, we will get root of 2VE divided by m. So this is the velocity. When you substitute this velocity in de Broglie wavelength of matter wave, then I will get the wavelength of electron. So we all know that the de Broglie wavelength lambda is equal to h by mv. So instead of v, we can substitute the value root of 2VE by m. So here h by m, instead of v, now I am going to substitute this, that is root of 2VE divided by m. Okay. Here this m can be, we can take it inside the root, so that it will become m square. So lambda is equal to h by root of m square. So take this m to m inside the root, so that it will become m square 2VE divided by m. Here we can cancel one m. So the remaining terms are h by root of 2MEV. So here we will have one more m. So 2MEV divided by, so that's all. So 2MEV. So lambda is equal h by root of 2MEV. So lambda is equal to, here substitute the values of constants, where h is equal to 6.626 into 10 power minus 34 divided by root of 2 into, where m is the mass of electron, so 9.1 into 10 power minus 31, and the value of electron is, charge of electron is 1.6 into 10 power minus 19, and capital V, where V is the potential difference that we can change. So when you substitute all the values and solve the problem, then we will get 12.27 angstrom divided by root of V. So this is the wavelength of electron. Here when you accelerate the electron with the potential difference of 100 volt, when you substitute 100 volt, so 12.27 divided by root of 100. So root of 100 is nothing but 10. So 12.27 divided by 10. So angstrom. When you solve this, we will get lambda is equal to, so 1.227 angstrom. So when you accelerate the electron with the potential of 100 volt, then the wavelength of electron is 1.227 angstrom. 1 angstrom is equal to 10 power minus 10 meter. See here EV is nothing but is a kinetic energy of the electron. So this equation can also be written as, so lambda is equal to h by root of 2ME. 2ME or 2MK. Some book they will use K, some book they will use E. Okay students, let me stop up to this. We will see the remaining in the next class.